Welcome to a read along with Dr. Powell on the book Discrete Perspectives in Mathematics. This is section 6.3. We're going to talk about how we can use the incidence matrix of a digraph or of a graph if we turn it into a digraph um, in order to study things about that graph or digraph. Now, what is a graph? A graph is something that doesn't have directed edges necessarily, or it could have directed edges. Digraph specifically refers to when you have directed edges. Nonetheless, look at this graph and notice that it looks like it's split into two different distinct parts. These are called connected components. There are two of them. So these vertices are connected via paths of edges to each other, and these ones as well. So there's two connected components. Now we can actually count how many connected components there are of a graph by studying an oriented incidence matrix. Let's first build some ideas. Okay, let's turn everything that we're dealing with into a Z module, meaning you see all these vertices. Let's think of them as being like standard basis elements of some sort, and we can be thinking about multiples of them and adding them together. It's a little, abstract from what the graph is, yet it enables us to be able to study things about this graph. So we're turning this graph into somewhat of a Z module, and then we're going to be doing operations on that to figure out what's going on. In fact, we could even change it to a Q module if we allowed for multiples of vertices that are fractions. And then you'd actually have a vector space. And so at the beginning here, we're just considering it as a Z module, but then we'll build that up. So we're going to create a merge, a function, surjective function that merges things together and chunks things up in a way that preserves the Z module structure. And how are we going to do this? Let's merge together. Let's see. If we propose, let's see how we're doing this. If we propose the two vertices, 2 and 1 must be merged, then we are saying we can replace V2 by V1. The effect is to say that even V2 minus V1 is going to be equivalent to 0, like this. This is kind of what we're saying. So after the merge, the 0 is going to be representative of V2 minus V1. They're going to be merged together. All right. So let's suppose if we merge V1 and V2 together, and if we merge V1 and V3 together, okay, like this, then we would know similarly this would be in 0 bar. So 0 bar contains these guys, and notice that 0 bar necessarily will also contain V2 minus V3, which forces V2 to merge to V3. So we have merging, it will be somewhat transitive, because if we especially if we think of this merge as preserving addition. So 2 and 3 must be merged as well, even if 1 and 3 is merged. And part of that comes from the fact, so as we move along, let's just kind of see this. All right. How did we make our original assumptions of what we were merging together? Like we wanted to do V1 and V2, V1 and V3. That was, we were choosing to merge things to like a vertex to another one if there was an edge between them. So we merged these two together because there's an edge between them. We merged these two together because there's an edge between them. But because the vector space operations, outside scalar multiplication or addition, are preserved, in fact, it was just addition preserved, that actually forced 2 and 3 transitively to also be merged together. So pretty much this process actually enables, if we just say merge two things together if they share an edge, what happens is in the final merge, the chunks actually represent the connected components via that idea. And in the next little subsection, we'll actually figure out how many connected components there are by considering the idea of dimension. Thanks for watching.